Yeah, am I more hearable now? There we go. All right, cool. Well, thank you all to the organizers, and particularly Martin and Cleona for this opportunity. I'm going to talk about NAMs and in silico approaches to the KCs, and I'm going to go ahead and skip ahead to tell you what I'm going to talk about, and I'm going to go through a couple examples and then come back at the end and revisit. Um, what I really like about the key characteristics concept scientifically is that it is modular. So I think a credit to what Martin and others, when they developed it, did was that they thought of something that was beyond the problem directly in their faces. And I really like the idea of frameworks and things that you can use to solve more than one problem or that accommodate the data underlying the particular question changing. And I think that's what's really powerful about the KC method. So I'm going to just talk about one aspect of it here and how to use NAMs and in silico methods, and that's the idea that the KCs offer an organizing framework for evaluating NAM and in silico data performance across bioactivity classes. So what I'm talking about is this. We have, at this point, several published key characteristic sets, carcinogens, endocrine disrupting chemicals, hepatotoxicants. You're going to hear about some of them in those sessions later this afternoon. But what we can do with any of those sets is cluster chemicals by KC bioactivity and maybe the more familiar cluster chemicals by structure classes. Those are related but not completely overlapping tasks. And I think Dr. Mansouri next will talk more on the cheminformatics side of things. But what I want to impart here is that you do each of these things perhaps separately, but then look across how they actually relate to each other, right? So they can inform upon each other if the data are organized in a useful way, which is what the KCs offer. I'll just highlight predictive toxicology needs some sort of framework for evaluating any of the questions you're going to ask with some tool like that. I think the KCs offer that, and they're modular and agnostic chemical set. And then lots of work, some of these were cited by Dr. Guyton's presentation earlier. Some new work, data packages, frameworks, weighting schemes. There's lots of those, and once you've chosen one, you can use these KCs themselves to evaluate models. So I'm going to not go through what NAMs and in silico approaches are in depth. What I will say is that I think of them as ways to interrogate different levels of biological organization, right? So I've shown here on the far right, populations of people, right? So I think from this morning's sessions, some of Martin's work is concerned about stressors that affect populations, perhaps differentially, not necessarily chemical stressors, right? So those are big questions over here. NAMs aren't really directly addressing that typically, right? You have to kind of stretch the definition, I think, in silico approaches perhaps. But what we're using is asking something down at these lower levels of organization to ask something higher, right? And I think that the KCs very naturally cross those biological levels of organization as well, where they're actually thinking at more than one level. You may measure something at a particular level in a particular assay, but it's really indicative of something that's going on that's bigger. And I think in Dr. Tice's presentation, you saw the network diagram and Dr. Guyton's as well. There's lots going on, right? There's lots that you can build out of this, but using this framework is useful. So one idea of this, and this is I'm kind of like a practical coder-minded kind of person. I think of integration as what are we going to bring together into a data matrix, right? What is our file system going to look like? And when I say that you can use the KCs to interrogate these things, what I mean is that the mappings that people do, right? I can pick out any assay from any system at any level of biological organization and say, for instance, induces oxidative stress, so KCC5. You may be able to measure that in some zebrafish system, and you may measure it in different ways, right? There's multiple ways to measure it. It might be a direct measure of ROS. It might be some recovery from stress, right? There's lots of ways to do that. But the point is you can have, for any given assay, if it's relevant to this KC and has been mapped to it, I can add that to my data matrix. Same in vitro system, some perhaps more naturally, more directly, measurement of oxidative stress, I can add that to, right? So I have these two different pieces of information, but they're informing on the same thing, organized by the fact that they're mapped to some key characteristic, right? So as the NAM set grows, I can map more. And as the KC set changes over time, I can adjust this a little bit too, right? So we're thinking of tagging things, not necessarily coloring things, right? It's not painted with one color forever. It can carry more than one tag at a time. So once you've done that, you can systematically ask questions of any, nameable stressor, right? So some stressors are, you know, you're not going to be able to subject them to some measurement in a dish, but anything, a chemical stressor, nanomaterials, even some sort of, temperature things you can think about doing in some creative way. I have them broken out here into in silico models, in vitro assays, and in vivo sort of endpoints. But as I think about the diversity of what you can measure with that, if I take any one, in this case, nanomaterial, and I look across, so I have a little arrow going from silicon dioxide, silver silicon rather, you can ask questions about any one ENM, right? So NAMs can ask questions about one very focused thing at a time with this organizational framework. Does it induce oxidative stress? I can also ask if these effects persist across levels. So that's a little bit of a higher level question. Then I can go down, and now the power of these higher dimensionality data sets is that I can start asking questions about sets of them. So do they drive stress in multiple cell types across classes of ENMs, right? Or if I've got chemicals across classes of chemicals, right? So now I'm kind of crossing that structural classification with the biological classification, but it's fit for the purpose of the question that I'm asking, right? I don't just have to ask one question with these things. I can organize these in a modular way. And if we can, the last one is the exciting one, can we predict bioassay results for things that are as yet untested in specific assay sets, right? So that's, if I have this framework and I get new results, I've already done my evaluation is set up for me, right? Whereas if I set up the model after the data come, well, that's different. That's a different exercise. So you can use them also, I think, to ask new questions, right? So using the same idea, right, where we're asking kind of the straightforward question of, all right, full rank data sets, I'm going across this, I'm building some sort of multivariate model. If I use them to ask, breaking apart these data into little pieces. So this first one is a CGAN is a popular technique right now that is, you can generate sort of fake instances of something. So photo recognition, you can train a learner to generate a bunch of things of my face that are not quite my face, but close to my face, and say, how well does it predict how close it is to what is my real face? You can do that with chemicals too, right? So a creative chemist can imagine, add any sort of functional group onto something or take something away, change the backbone a little bit. We can do those kinds of things and evaluate them in this namespace mapped to a particular KC. I can use it to evaluate missing data. And I think this is something that keeps coming up in the discussions yesterday as well, is what does our coverage look like? Like, do our assays cover the set that we need? And how can we decide what new assays to be either developed, or if they're already existing, how do we pull them in and use them in this model evaluation? And I can do that in a formal way. If I have things mapped beforehand, I can already say, well, we're missing sums on this particular KC, for example. And the last example here would be a feature identification and trying to identify the drivers of activity. So there's fancy AI/ML models. There's more traditional statistics that are useful here as well. And trying to figure out which things of my feature set are actually most tied to a particular key characteristic, right? And I can ask that question in a very formal way, and I can not just get the answer, but I can assess, is my answer of high enough quality that I want to believe it, or do I need more information? And this is my last example slide here is, and this is a paper that Kate cited, and it's led by Wei-Shui Chu, and Yvonne is a co-author on this paper as well. This was from the IARC monographs on an application where, here are 6 of the key characteristics, mapped in this particular weight of evidence scheme. And the reason it's useful is I have a list of however many chemicals in panel either along the y-axis, and I've highlighted the ones that have the ToxPy diagrams on the left there, the exploded radial charts. And I can do this with an arbitrary set of chemicals, right? So I can change both the data and the chemicals and ask, are the things that I think should be lining up at the top actually lining up at the top? Are the ones in the middle lining up in the middle? Are the ones at the bottom lining up at the bottom? And that helps us assess the coverage of our particular chemical set and the assay set as well, right? So this is not a clustering based approach, but clustering in the sense of, are the things that I'm expected to be most active becoming most active here, or in the middle, are they low, right? And you can see how if I'm doing model tuning, these are the levers that I can use to give me evidence of how to tune these things, right? Once I have them mapped in the key characteristics, which gives me the biological knowledge to organize and annotate these data, right? Because using all the data every time is just noise, right? That's not, none of these HTS data sets were really designed to do one thing. You know, many of the most popular ones are kind of an assembly of, I don't want to say convenience to disrespect them, but what was available, let's bring it in, rather than I have a problem I want to address, right? And the KCs offer a way to organize that knowledge that's modular. So to roll back again, you know, going backwards, there's lots of work on schemes and evidence and ways to build these weight of evidence models. And I think they're all offering something useful, right? But the idea is that once the data are organized and tagged, you can use these to start saying, is my tagging right? And are my data correct, right? And the same for these predictive toxicology applications. These are agnostic to chemical set. So I can have a new chemical set or a slightly modified chemical set, or throw in a bunch of, whether it's metabolites or related compounds, and ask how things are performing, right? In a sort of clustering, like is in here in the middle, or I can add new chemicals in from a particular structural class and ask, is that being recapitulated here, right? But I think that the growth here, and I think, you know, this is the most recent of these, was listed as 2021. I know there's a bunch more in the works now, right? So as that catalog grows, I can really think of having a very powerful set of being able to interrogate the bioactivity that is relevant to humans of chemicals, using this kind of framework, using this modular framework. And I think that's where the NAM space and the in silico space can offer some benefits in this area. So, yeah, so that's all. Thank you.